So we're talking about functions and their inverses today. So not all functions have an inverse. So there's kind of some requirements to have an inverse. So the first one is that every element in the domain is paired with only one element in the range. Let's see if that's true here. So there are three elements in the domain that each are paired with only one element in the range. So this is a function that passes the vertical line test, so to speak, there. So if these were graphical points, like ordered pairs, 2, 7, 5, 7, and 8, 3, it would pass the vertical line test. So to be a one-to-one function, which is very special, it first must be a function. That's just a test, is it a function or not? And to be super special, every element in the range is paired with only one element in the domain. Let's see, there's two elements in the range. This 7 is paired with both 2 and 5. So this function does not pass the horizontal line test, does not pass the second part of the test. And so this particular function would not have an inverse. So let's look at this and see if it passed both tests. So every element of the domain, all the x values have a unique y value. If you took a vertical line and you just kind of passed it along here, it crosses only at one point at a time. So that definitely passes the horizontal line test. If we move that around here, let's see, let's try this. Let's try a horizontal line. So draw a horizontal line and move that, you can see that, this doesn't pass the horizontal line test. So it crosses at more than one spot. So this one is not a special function. You can see that it crosses at more than one spot there when you draw a horizontal line. Inverse functions, we have a unique way of writing these. So when we write this f of -1 here, it does not mean this. It does not mean a negative exponent there. So don't think that it does. It means the inverse of f. That's just a shorthand way. We're mathematicians. We like to write things in a quick way. And so that notation, and when we're talking about functions, it doesn't mean exponent. It means the inverse of. So it's a quick way of representing that. So let's learn graphically what an inverse function is. I think it's the best way to kind of learn about an inverse function is look at the graph of a function. So let's identify some points on this graph. So x, y. So some nice points here. It looks like it crosses through at 2, 2 is one of the points. Let's see. 3, 4 looks like a point. Looks like 4, 6. This is 1, 0. Probably see a pattern here. 0, -2. -1, -4. And sure, one more. -1 there. And then -3, -6. So we got a bunch of points on that. So there's a special line here called the identity line. So this line has a slope of 1 and a y-intercept of 0. So it has a slope of y-intercept of 0. Slope is up 1 over 1, up 1 over 1. So you can see this kind of crosses the uprights there right in the middle. So it just kind of at a 45-degree angle. That's the identity line. And inverse functions are reflected across that line. So if you take these points and you reflect them, so see what would happen. Like if this point was reflected across the line, it comes to this point. So it'd be the point 0, 1 is that point right there. If we reflected this point across the line, it looks like it would cross like right to there. It goes from here to there. So that's the point -2, 0. Here, this point, if we reflect across, it looks like it goes to right there. This point would map, if we reflect it across that y = x line, it goes to -4, -1. And this point, if you move it, it looks like it crosses to there at negative 6, comma negative 3. What's interesting, this, if you kind of reflect it across the line, was right on the line, so it just stays there at 2, 2. Doesn't move at all. This point would reflect down to here. You might see a pattern forming in this line here. So that would be the point 4, comma 3. And finally, this point would reflect to right there, which is the point 6, comma 4. And so pretty soon we've got this line here. So that's the inverse. This is the inverse of f of x here. So if f was the green function, then the inverse is the red function here. And you may notice something else about the red function. It's kind of neat when you notice this. What's the relationship here? That's the ordered pair of 4, comma 6. This is 6, comma 4, right? 3, comma 4, 4, comma 3, 2, 2, 1, 0, 0, 1. You can see that basically what happens with the inverse function is the x's and y's switch places. It's very important that you kind of get that idea there. So the x's and y's really are just switching places. So here, when we see this, we know that this is essentially a point. We plug in an x value, we output a y value. So that ordered pair would be negative 1, comma 4. Oh, sorry, negative 4. Then, well, what would the inverse of f of negative 4 be? So what's interesting with the inverse, so if we plug a value into here, what's the inverse of negative 1, negative 4? It would be the point negative 4, comma, negative 1. So the output here is just negative 1. This point just flips around when it's the inverse here. So we're plugging in a y value, getting x value in a way. It's one way of thinking about that. So it's kind of a neat little thing you can do. It's almost a trick question. But if you know how an inverse function works, that the x and y is switching places, so now if I take the inverse and plug in that value, I should get what started out as being the x value there. So I want you to get the idea of an inverse. It really helps. We don't have to solve it this way, but the idea of an inverse, if f of x was 2x, then the inverse of f of x would be, what's the opposite of multiplying by 2? You would divide by 2, right? If f of x was x plus 2, the inverse of f would be x minus 2. It just kind of undoes whatever the inverse, whatever the original function does, multiply by 2, the inverse will undo it. Now sometimes it's hard to do when you're doing a couple steps, but there is a test we can do. If f of x undoes the inverse of f, so if this one multiplies by 2, this one divides by 2, you're just going to be left with x when you compose the two functions. Or it doesn't really matter the order. If you start with this function, the f function will undo. This was adding 2, this would subtract 2, and you're just going to be left with x both ways. So this is the test that we apply. We say, okay, this must be true of two inverse functions. So given two generic functions like these guys, sorry about that. Okay, so let's apply the test to these. F and G, it doesn't tell us they're inverses, but I'm going to guess that they might be, so I'm going to apply the test. So the test is f of the inverse of f. Let's assume this is the inverse. So I'm going to say f of g of x. If these are inverses, what should this equal? Well, it should equal x, right? That's what the formula says here. That's what the test is. Well, let's actually compose them and see what happens here. So f of, let's see, g would be 3 minus 4x. And let's just see if it equals x. Now we're going to plug that into the f function right here. So we're going to say 3 minus 4x all over 4. Let's see what happens if we can simplify this a little bit here. So this negative distributes to both terms. You get 3 minus 3, which is 0, and negative 4x is positive 4x in the numerator, divided by 4, and that cancels, and you get x equal to x. So we did get x. We wanted to test and see, again, on the right side here, we just have x. Did we get x? We did. Check. Oh, I have to do the other test as well. So we have to compose it the other way. So let's compose it the other way. So what is g of f of x? So in this case, we're going to plug f of x function in. So this will be g of f of x is 3 minus x over 4. And we'll plug that into the g function right here for x. So this would be 3 minus 4 times 3 minus x all over 4. And again, we're hoping this equals x. We're just not sure yet. Let's keep going. We hope this equals x. If this is going to cancel here, so we get 3 minus x. And that negative distributes to both. 3 minus 3 is 0. Negative x is positive x. X equals x. I've done both tests. They both work. So I can say that g of x is the inverse of f of x. So I just proved it. So we didn't know going in, but now we know. So we can also find a function, find its inverse. So we can also find a function from an inverse from scratch. So assuming that a function is in fact a one-to-one function, and this is, it passes the horizontal and vertical line test, then if it does that, we can actually just do this. It's a step, it's a process. So first step, replace f of x with y. So y equals 2x plus 1. Then you do the big idea of inverses, which is switch all the x's and y's. So this will be x equals 2y plus 1. Now we want to solve for y. Take a couple steps. X minus 1 equals 2y, divide by 2, divide by 2. I get y equals x minus 1 divided by 2. Last step. That is the inverse function, but I need to name it as such. Remember, f is the original function, so rename the function as the inverse. So this would be the inverse of x equals x minus 1 over 2. That's the basic process of finding the inverse from scratch for any given function, as long as it's one-to-one. Let's find the inverse of this one, right? So let's follow the steps. Y equals x squared plus 3. We're going to switch x and y. X equals y squared plus 3. We get x minus 3 equals y squared. Take the square root of both sides. Don't forget when you do that, you got to do plus or minus. And we get y equals plus or minus the square root of x minus 3. Now, that's kind of weird because we got two functions as the inverse functions. Something's wrong. Oh, I didn't notice this, right? Uh-oh. So the domain of the original function is x greater than or equal to 0. Well, let's think about what this function looks like. I think it might help to take kind of a graphical view of this. So the original function, x squared plus 3, x squared looks like this. We learned in transformations that if you move that up, that function is going to look something like that. And it doesn't pass, by the way, the horizontal line test, does it? So it's not a special one-to-one function. Oh, but it says the domain is really not any of these negative values. Really, this is the point 0, 3. And it goes up and to the right. That's like a really bad parabola, but it's a parabola that goes up and to the right. It should be a little bit more curved there. So that the domain is that. I'm just going to go ahead and write down the range here. It might help us. Range is from 3 to infinity. What's going to happen now is the domain and range switches places. So the domain of this guy is going to be 3 to infinity instead.